Hi, I'm Professor Santiago and we'll continue our discussion with Z-transforms. The last video was a basic introduction, and here we'll provide an example of an inverse Z-transform. So before providing an example of an inverse Z-transform, let's look at the Z-transform pair. So here in the time domain, we have a sequence described as follows: the summations of weighted time-shifted impulses, as shown here. Xk is the weight, and these are just time-delayed impulses that are added up from k equals 0 to n. Now its corresponding z-domain description is defined as follows, where we just take this sequence xn, substitute it in here, and multiply it by z minus 1 raised to some power k when it's summed from 0 to n. So this is just simply, once again, a polynomial of z minus 1. Let's look at some examples. Let's say we have just a single impulse that's delayed by n0. Using this definition here and substituting it in here, we simply get x sub z equals z minus n0. Just a quick note on delta functions. Say here that we have this single delta function with a shift. Alright, when we substitute it in here, that's just x sub z, and since there's only one term, there's no summation, so we substitute del k minus n0 z to the minus 1 to the n0 power. Now when you do delta functions, you only evaluate it when the argument of this delta function is equal to 0. So that means that this delta function, here's this delta function with a sequence with a weight of 1. This is our n domain, and this is our sequence xn delayed by n0. So when you do that, this delta function only exists at this point, n0. So therefore, when you do substitute this k in here, k is just simply equal to n0. So that's why this k right here is equal to n0. Hence, this function overall is z to the minus n0. So that's the beauty of delta functions. You just have to know that it exists only at one point, and so you evaluate that time domain or n domain at that single point. Set this argument of the delta function equal to 0. Let's look at another example. Again, these are z-transform pairs going from time domain to the z domain, and later on we'll provide an example going from the z domain to the time domain. But let's look at one more example. Let's say we have a sequence xn 2, 4, 6, 4, and 2. We can rewrite this as a whole bunch of weighted time-shifted impulses. So for example, let's say this 2, and assume that this is n equal 1. This is simply xn2 with a delta located at n equals 0. I mean, that is k equals 0 for this impulse. Our next one is 4 delayed by 1. That's shown here. And 6 delayed by 2. And then this one is 4 delayed by 3. And then finally this 2 has a weight of 2 delayed by 4. So these are just basically right here represents this formula shown here. Now let's find the z-transform of this. So the z-transform of this first term is simply 2 if we apply this formula here, which is really this formula in general, but we can use this as a baseline for each impulse. So here we have a delay of 1, so that implies that's 4 z to the minus 1. For 6 we have a delay of 2. Notice we have the same 6. That's the weighting function of this z polynomial of minus 1 raised to the second power. Then here we have 4 with a delay of -3, and then 2 with a delay of -4. So that's how you take the z-transform of this sequence and convert it into a z-transform in terms of a polynomial of z-1. So let's consider this inverse z-transform example. Here we have our n-domain description or time domain, and here's our z-domain. And let's say we're given this z-transform. Hopefully you see the pattern now. 1 minus 2 z minus 1 plus 3 z minus 3 minus z minus 5. Okay, so let's take a look at the first term. So our xn would be, first term has a weight of 1, z to the 0. Here we have the second one, that is del n, no shift, minus 2. Then we have a shift of 1, so del n minus 1. We don't have any z minus 2, so I'll just put this for emphasis so you can see that. So it's 0 del n minus 2 plus 3 del, right here, n minus 3 plus 0 del, since we don't have z to the fourth, so this is just del of minus 4. Then finally we have z to the minus 5, which is negative 1 z del, n minus 5. So that's our description for this sequence going from here to here. But these, as we note, are z-transform pairs. So that concludes this example, and next we'll talk about the z-transform and linear systems.